Okay, day 39 notes for college algebra. Sorry I couldn't be in class today. My goal was to be there and complete an experiment together in class, but I was not able to make it in. So in this video I'm going to walk through half of the experiment, the data collection for hot liquids, and hopefully tomorrow when I see you in class we will be able to do the cold water data collection together. First thing that I'm doing here is just rereading the instructions. We're investigating the graphs of the temperature of hot and cold water, and using our knowledge of exponential functions, we're going to determine the amount of time that it would take for water at an extreme temperature, either hot or cold, to approach an acceptable temperature, something that we could drink ourselves. So what needs to be done first, and you'll have to do this tomorrow when we take our data collection values together, we're going to turn on the NSpire calculator. Now, I believe the thermometers that I have won't plug into the calculators, but they will do so on the computer, just like the one that I'm using right now. So all of us have a copy of the NSpire calculator installed on our computer, so that's what we'll be using. When you insert the temp probe into the USB port, a new document is automatically created, and the current temperature should display in degrees. It'll look something like this. Now I need to adjust my window, so bear with me for just a moment. Okay, that looks a little bit better. It fits the screen, and the text is a little bit larger. Now, you'll probably have to do this, but I've already made the change on my computer. We're going to adjust the rate by clicking on the box, and we're going to record an interval so that information is taken every 20 seconds for the duration of 180 seconds. We're going to record a change in temperature for about 3 minutes. So this interval box, when you click on it, I think by default you'll see rate, the number of samples per second. We're changing that to an interval, so the number of seconds between each sample, and we're going to collect data points every 20 seconds. Okay, so as far as the data collection goes, we have to of course be very careful with hot water. I don't want anybody to hurt themselves if you're performing this experiment on your own. We've got about half of a cup of hot water into a vessel. Now I had coffee being made at my house here, and I took some hot water from the coffee maker, and I've got it into a Yeti cup right now with a lid on it. So the first thing that I'm going to do is make note of the ambient air temperature. What's the temperature inside the room right now? And right now my thermometer is reading 25.1 degrees Celsius, so I'm going to make note of that. I'm going to ask that you copy this down as well. Next, I'm going to place the tip of the temperature sensor into the cup and wait at least 60 seconds for the temperature to acclimate to the hot water, and we'll make a note of the temperature of the water. Soon after that, we'll remove the temperature probe from the hot water, and before you remove the temperature probe from the hot water, I want you to make your prediction of what the graph will look like of the temperature reading against time. So again, we're going to bring this thermometer up to temperature. We're going to pull the thermometer out of the hot liquid and let it just rest in mid-air for 3 minutes. What would the shape of that graph look like in 3 minutes time? We've been studying exponentials, so I want you to think to yourself, is it going to look like this? Might the graph look something like, oh, I don't know, this? Is there another combination that it might appear? I don't know, but make a guess. What would the graph look like? Just sketch that here. Make sure that you do label your axes. So I'm going to ask that you pause the video and create a picture, and when we come back in just a few moments, replay the video, and I will get this thing set up so that we can record some data points. Okay, so the thermometer has been in this hot water for about a minute now. while I pause the video, and I've gone ahead and sketched what I think my graph is going to look like. As time increases to the right, I know that the temperature will fall, so my guess is that the graph is going to look like this. Hopefully you've made an educated guess as well, and we're just about ready to begin. Now if I flip over to the thermometer here, the water temperature has leveled off at about 47.8 degrees. So we'll note that, 47.8 degrees Celsius. And in just a moment, we're going to press the play button to record data. And at the same time, pressing the play button will remove the probe from the hot water and hold the probe in mid-air. We don't want to rest the tip on the table because that would give a false reading. The calculator is set up to record temperature every 20 seconds for a total of 3 minutes. So yes, we are going to sit here and watch this device take temperature readings for 3 minutes. So without further ado, I will begin. Feels like we had to wait an awful long time for that first data point, but do keep in mind we're only taking data points every 20 seconds, so there are going to be large gaps, but hopefully the shape of this graph will present itself after just a few data points. So we're a little bit more than a halfway into this. It looks like my guess was no good. After all, I thought this would be a linear drop in temperature, so evidently my graph doesn't work. Hopefully you made a better guess, and with any luck, your guess is starting to look like what's appearing on the screen. We've got about a minute left. Okay, we're coming up on the end here, and there it is. So at the very end, the calculator does resize our window a little bit. I want you to be careful with what we see here, though. You'll notice that the temperature of the probe was approaching room temperature, whatever room temperature was. This picture, however, is a bit misleading because it does look like we're approaching zero, approaching an x-axis, and that's not really what's happening. We had that vertical offset to contend with. So right now we're in data collection view. If we click the table view here, we'll have the temperature for each of the intervals that we recorded. I'm going to take a second to copy this information down to the worksheet. Okay, so I've copied the data values and placed them in the table down here, and I'm also plotting those points against my guess, and I would recommend that you do the same. Now would be a good time to pause the video and copy the collected values and take a look at the scale that I've applied to my XY axis up here. Why don't you add that to yours as well and plot these data points if you haven't already done so. Now I'm going to sketch in a line connecting these data points. It doesn't have to be perfect, but I think a good representation would be fair. And I'm starting to see that, well, my linear guess was no good, of course. But this thing does resemble an exponential decay problem that we've seen before, an exponential decay graph, I should say, that we've seen before. Okay, so as I said, I'd like to do the cold water data collection in class tomorrow, so I'm going to skip down to some questions at the end of the second page. I don't believe this page got copied on the handouts that I gave you today, but that'll be okay. We'll look at them tomorrow. To summarize the data that we've collected and to make use of the calculator that we have, we're going to press the Control key and then the Dock button to add a new page. And then we're going to choose option 5 to add a data and statistics page. You can see that the data points that were collected by the calculator are scattered all over the place, so we need to specify an appropriate x-axis variable. I think time would be appropriate for that, and the same for the y-axis. Our goal is to get these scatter plot points more in the shape of what we saw on the graph just a moment ago. And again, this looks pretty good, but we do have to be careful here. It looks like this graph is tending towards 0, towards an x-axis asymptote, but we do have to pay close attention to our scale over here. This graph is not leveling off towards 0. Now, for part 3, we're going to have the calculator find an exponential equation for this data. We'll do so by pressing the menu button. We'll choose option 4 to analyze the graph, option 6 for regression, and then option 8 for exponential regression. Okay, well there we go. Here is the supposed exponential regression that matches the data points that we have here. To me, that's not a really great fit, but supposedly, according to the calculator's algorithms, this is the best equation that works. So we're going to write it down, and I am going to round these results to 4 decimal places. Okay, so hopefully you feel as uneasy about this as I am, and there really is one glaring problem with this particular example. If we copy down the formula, we have a calculated C value, 40.6125, and we have an A value of 0.9968, and the question becomes, does the C value seem appropriate? Does the A value seem appropriate? And I want you to think about why or why not these are any good. But the glaring problem that we have here is the issue that we talked about yesterday in class. The formula here would be good if the temperature was reducing to 0. If we started at 40 degrees and we reduced to a temperature of 0, that graph or that equation might make sense. But we weren't approaching 0. the graph was leveling off towards some horizontal asymptote. There's a constant b value here, a constant height to this graph. And this exponential regression did not model that b value. And so, since this video is starting to get a little bit long here, I want to stop and leave you with a challenge. With your knowledge of exponential functions, I want to see if you can make a better guess. What would a better formula look like that incorporates this notion of the b value? You can look at sample questions from the homework over the weekend when we were talking about Newton's law of heating and cooling, or you can look at the notes from yesterday in class when we have specific data points. Can we use those data points to establish an appropriate c value, a, and then how would it be modified for b? And I suppose a better example might be this one. This is the one that we did in class yesterday. So think about it. Can you make a better fit than what the calculator has presented? We'll talk about it next time I see you in class. Good luck.